So Alex could not make it. He had some last-minute commitments in New York. He wishes he could be here. So I'll do the talking instead. So I thought. Okay, so the title is perhaps a bit deceptive in itself. There's nothing being stolen more than any other location that would experience a subprefix hijack has anything stolen. The interesting stuff here is going to be talking about more interception. So if I could have retitled the slide and got it to the presenter laptop in time, you would have seen something a bit different. So I'm going to go through a few simple points first before getting into the meat of it, and I'm going to assume that everyone understands basic stuff about BGP and has familiarity with the concept of a subprefix hijack. We're not talking about the details of that. We're talking about the implications of in the interception potentials. So first, we're going to talk about a few points and people who have talked about this and a lot of theory that has been spun, and then talk a little bit about the actual application mechanics of this particular operation, and then talk about a bit of what we can do to stop it, perhaps ask for more support from the community to continue to push the further development, and then a little bit of an analysis of what we did at DEF CON. And I think that's probably the more interesting piece that folks have requested in this talk. So ultimately, if you hadn't heard yet, this is perhaps a bigger deal than other types of subprefix hijacks in the sense that essentially in a blind scenario with no coordination at either the attacker's network necessarily or definitely the attackee's network, you can attract traffic and bring it right back to that network. And that's, that in itself is not terribly novel, but in the mechanism we'll describe, nothing had been demonstrated to our knowledge of a similar form. The other important point is that to solve these issues requires direct attention. Any providers who are doing adequate filtering now, you're not interesting to this, but the people who are not, and the people who do not have adequate alarming systems in place or interest in generating them are going to be the ones that ultimately help allow the riffraff in, if you will. So prior work, important to cover. So the NIST report from last year essentially just states quite generically, yes, it can be done. We can intercept traffic somehow. No one could say how. The most recent discovery I had made was of a particular paper from Paul Francis at Cornell, and he was using a mechanism that essentially pretended to be, or would have rather been appropriate to do at a tier 2 type network, somebody with several hundred edges. And his paper essentially says that if you swim through AS path alone and do not do subprefix hijacking, you can actually do that successfully, and then also how much edge capacity would you need, or rather how many edges would be required to net significant amounts of traffic. So interesting approach, but not necessarily like this. The next most near match to this kind of a topic was one from UIUC, and this one was discussing essentially by positioning oneself or finding a network that is ideally positioned, what could be done using essentially traffic engineering techniques to both intercept the traffic and re-deliver it to the intended destination. So interestingly, none of these discussed creation of a path, what we will call in this presentation to be a feasible path back to the target. Again, we're not talking about, and I don't want to discuss the particulars. I mean, getting a route out there is plain and simple. IRR updates aren't secured. There's a lack of trust from the top down. We all know that. The interesting stuff here is that we can create these selective black holes through typical techniques we've already been aware of, and facilitate some interesting interception potential at a large scale, and from essentially any location to any location. The other points we'll discuss, and the other thing that's perhaps half novel, partially novel about this, is that by applying TTL additions to packets in flight, the entire topology, the layer 3 topology, the data plane topology, is effectively invisible to points that are trying to probe perhaps traceroute, and tools like that. As far as hiding the hijacker, if the origin route contains an AS path naming ASs of known monitoring ASNs, and if those said monitoring ASNs are employing standard BGP path logic, they would not accept these routes with AS paths that name them because of loop detection as well. So if we knew of the dozen or handful sites that were monitoring and setting alarms, they perhaps would be thwarted through this technique by including them in the path. We'll talk a bit more about how that might be applicable. So what is the concept at large? What is really happening? So to successfully intercept data, you have to both bring it in and then, again, pass it back somewhere. And the interest here is in getting it back and then not breaking things. So we have to create this path. The question is how? And the papers discussed prior had techniques for this, and some of them were, shall we say, non-trivial. There was work required or coordination required. This one doesn't require that. So how do you create this path back? Well, first, figure out what the path from you, the in-place forwarding path from your network, from the attacker's vantage point, towards a particular target is. Do you forward through any particular upstreams? If so, of course you do. If so, then track what they are. If you forward to upstream A, then to B, then to C, note this. You're going to need to maintain that. And I'll diagram that in a short moment. Again, the ASNs are what we need to know about. If you transit through Sprint to perhaps peer of Sprint to the end user, those are going to be the ASs that we have to eventually black hole to use as our return path. So essentially the point is the in place right now forwarding characteristics must be maintained or else you don't have a deterministic result. So in the hijacking then, the application of the AS path prepends must include this set of ASNs that you already see back to the target. Again, these are going to be the maintained in-place forwarding elements. Now, once the traffic is arriving, once the hijacked route has been sent, we need to then take the packets that had been received for that particular target prefix, and again, shoot them down this feasible path. So a U-turn, if you will, a hairpin, has to occur in our attacker's ASN. And then after we do all that, we go upstairs. So how does this look normally? Let's watch a route propagate from the target ASN 200. They're going to originate a /22. And we see that route propagate, layer by layer, degree by degree. Eventually the attacker hears that route and says, aha, they have a 22. The forwarding table that would be resulting from this would look as such. Now the interesting thing we have to maintain here is the path we've currently selected. We want to continue to use 10 and 20 to reach 200. So if this 22 was going to be subject to a sub-prefix hijack, say a 24, we would have observed that viable path and continued to want to use it. We would then build an AS path list, or rather a prepend rather, to attach to this /24. And so when that 24 is announced, perhaps the font's too small to see, it would be appending to the right of 100, 10, 20, and 200. So what this would effectively do is prevent AS20 from learning that route via 30 or anybody else they're adjacent to, and also prevents 10 from learning it from us. You can kind of let 30 and 40 in your minds represent the other 30,000 some ASNs out there. 10 and 20 could be neighbored up to every single one, and if their AS number again is in the path, that's going to fail checks unless they've disabled that check. So we announce route, said route goes out, and the forwarding path that we now observe, the forwarding table we now observe in all the coordinated routers is what we desired. We wanted 30 and wanted 40 and wanted the rest of the internet to send traffic for that 24. Again, longer prefix already won that to us. But now, because 10 and 20 have not accepted our route, all they have in place in 10 and 20 is our /22, as learned from 200. Therefore, they continue to forward this back to 200. And this is the essence of the BGP man in the middle. This perhaps was the part that was not well represented by previous reports and news articles and things online. So again, the traffic can U-turn through us and we don't break things. We miss, of course, traffic from 10 and 20. So if those were exceptionally large ASs or customers of those who weren't singly homed, or rather who were singly homed, we wouldn't get that traffic. The attacker in ASN 100 would only see traffic minus the feasible path back to the target ASN 200 here. So once the traffic gets to us, of course, to facilitate the U-turn, toss a static route in. So at DEF CON, as a small summary, the timestamp in epic seconds at the start of the hijack was 252 ASs reporting the /22 at the conferences network. And within 80 seconds, 94% of them carried the hijack 24. And the difference, could be a policy issue, could be customers who were somehow singly homed or somehow not getting the hijacked route from a feasible path that we had used. Not sure. Interestingly enough, it was somewhat successful in this particular metric. Everyone likes graphs. I like academics too, so I decided to get one of the time series. This one will show on the right x-axis the number of ASs reporting having heard the 24 at a certain timestamp. The delta from origin first heard, rather from the first heard announcement, is in seconds across the bottom, and the leftmost axis is the accumulation on the green line of ASs that have been ASs that would have been heard, percentage of total that would have been taking the route, and you can kind of see evidence of MRAI having done its job. So again, when the route's announced, it's fairly quick. We all know that, but if you're near the core, you can insert the hijack route quickly, and it doesn't disrupt things. Again, as the route propagates from the point of view of the attacker, everyone's forwarding to you as each degree transfers the route successively. So essentially, the attacker can insert themselves into the inbound path of a particular prefix and not disturb anything, which is unexpected in my mind. You definitely will see, and we did observe at DEF CON, that when the route was removed or withdrawn, microloops would cause momentary outages for the next number of minutes until things converged back towards the original origin. So essentially that method then means we have, I think, yet one more reason than just observing outages like YouTube last February, to look and to re-examine ways to solve or ways to perhaps pin trust on the apparent origin of a particular prefix. And I think ultimately this means we need to step it up. We haven't done this in 10 years. I don't want to get up here in the next 10 and still see similar issues. I'd like to have this solved. I guess, of course, we heard a discussion about securing the root prior, and I'd like to hear something similar, more about securing things from the point of view of RIRs. So perhaps the half-novel portion will be interesting to talk about. The way that we did this at DEF CON was of course to attract the traffic, but that wasn't cool enough because it reveals a long trace route without doing anything about it. So essentially, Alex's network originated this /24, and from the point of view of a router on a Chicago transit link to AT&T was taking a detour, of course, into Savvis, then to New York, then to Palosoft, and then the static route back out was through NLayer towards Limelight and towards then Switchcom. By adding values to TTL upon ingress, you can then effectively hide all of that. And this is a trivial thing with IP tables. It's an increment command. Add some number to it. All of a sudden, trace routes don't reveal you. So with an adjustment, the hijacked route is 13 hops. You could have made that arbitrarily short. Could have been 10, whatever. Could have hidden all of the ingress paths to Switchcom group. But again, the original went from AT&T to Limelight. The hijack now goes from AT&T to Savvis to Switchcom. And there are no observed edges anywhere on the internet between Savvis and Switchcom, behind Savvis that is, but to anyone doing a trace route, this isn't obvious. You'd have to have a view somewhere. ideally someone looking at things to secure things would do more than just look for subprefix hijacks or subprefix origin changes, but also something that would look at perhaps a tomography or a topology approach to pinning down the intersection of, does that edge that we see or we elicit really exist in routing? Could be open to a lot of interesting, perhaps, research. So the default way to originate a prefix, of course, would reveal your, or rather the attacker's, origin AS in the path. A friend had turned me on to the point that devices that support transparent AS, or rather software daemons such as OpenBGPD, Quagga, can send routes with any apparent origin AS. And if your neighbor's not enforcing next AS, on the neighbor session, they'll accept this prefix, they'll accept this advertisement without any troubles. So perhaps the attacker could even be completely opaque in the origin of this subprefix. If you had perhaps a session to your transit configured as reflector client or route server client, as you went at, say, an MPLA style route server based exchange. So this opens up yet one more avenue for being somewhat stealth. Again, this will not make any sense from what a real relationship would reveal if you could examine the actual data plane at each particular adjacency. And again, this could be an avenue for detection as well. So, shorter talk than perhaps we had planned. I think we have time for some questions, certainly. But I guess all I wanted to summarize by saying was that this is pretty stealth, can be nearly invisible, yet you'll still see some disturbances from the point of view of a subprefix hijack. If we consider some of the papers, especially the one from Cornell, we know that we don't even need to win with subprefixes. If a certain network were co-opted, this could be done without subprefix hijacks required. Subprefix wouldn't even matter. We would just win through edges. And if you won the right edges for whatever the purpose was, then the need is served. We know that, again, path isn't going to be the only telltale, but it could be massaged. So we can't depend on that alone to perhaps detect it. So I think this points to a combination of mechanisms required to adequately protect this or alarm on it. And bottom line, filter your customers, turn on NextAS. It's on an iOS by default. It's probably good to turn it on if it's not older software. And that's all. Any questions? Ivan, Randy? All right, thanks, guys.
Thanks, Tony.